Yeah, welcome back. So far, we have covered two things: singular value decomposition and, principal component analysis. In the light of what we have covered, because some of the things we kind of hand waved in the sense that we assume that some of the things we already know, but just to refresh your memory, I think it's important that, we revisit some of these ideas and, some of the ideas that we have particularly used. Like we have seen in singular value decomposition that we use the idea that orthogonal transformations are matrix preserving, angle preserving, right? And also you have, you can use the idea that, eigenvalues of a real and symmetric matrix are, distinct, and eigenvectors corresponding to real and distinct eigenvalues are, orthogonal to each other. A set of orthogonal eigenvectors are linearly independent, and so on and so forth, right? Okay. And also the whole idea of eigenvalues, because when you talk to people, everybody, even if you ask me, what is an eigenvalue and eigenvectors, these play a very critical role in determining or shaping what we do, particularly in machine learning. Okay. In fact, there is a whole area of spectral clustering which leverages these particular ideas, right? So, what really does the eigenvalues and eigenvectors mean? I have told you in the previous lectures that, the whole idea behind that Tx equal to lambda x equation is that, you kind of generate a matrix vector product such that the output does not fall off the span of your original vector. Okay, all right, because you can do a bunch of things with eigenvalues, right? You can rotate, reflect, translate, blah, 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 you do a lot of things, right? Just for a quick recap, we use, as I said, right, in singular value decomposition, that the different matrices, the matrix P, when you do that, eigenvalue decomposition for a square matrix A, and the matrix U, which you do that the singular value decomposition of the non-square matrix A, they do not share the same basis. Okay, all right. So what is a basis? Okay, what is rank? What is a row space? What is a column space? Why do we care about this? What are eigenvalues and eigenvectors? What are their true interpretations? Right? Okay. So let's begin. Okay. So we know that we have let's say a linear transformation from an Euclidean space of n dimensions with the real numbers, Euclidean space of real numbers. So basically a real vector space, okay, in such a way that we have this particular relationship, which is explained. Okay, so what does this really mean? When your vectors also come from the n dimensional Euclidean space, okay. All right, so this could be reflected around a line, the coordinate axis, rotate, blah blah blah, but bunch of things, right? Okay, so what is the true implication of this? And from this when we actually compute the eigenvalues, where did you see this? If you recall, we saw this in principal component analysis, right, where we were computing the eigenvalues of messages sent and messages received, right? Why do you compute this determinant? Okay, in this context, I would actually, ask you to visit or, read two books which I follow closely. Both are by Sheldon Axler, that's the author. Down with Determinants. And the other one is Linear Algebra Done Right. The titles seem a bit audacious, but let me tell you, I haven't seen better books on linear algebra than written by this author. Okay, all right. So what is a span? You know that you think about a two-dimensional space, right? a three-dimensional space. Let's say we are in this particular recording room, right? And I can imagine I have a vector. Right, I have a vector 1 0 0. I have another vector 0 1 0 and another vector 0 0 1. Okay, all right. So there are three guys. What can you do with this? Now these are what? All of these guys are unit vectors. These are unit vectors in the direction of x-axis, y-axis, and z-axis, respectively. Right. What I can do is I can multiply each one of those by some arbitrary number. You can think of a positive number, you can think of a negative number, right? As long as these are real, correct? Okay, so now, so what you do is, I mean, when you do that, when you multiply each one of these guys by some arbitrary real positive or negative numbers, and then you take the sum of all that, what do you get? You actually get a point, any point, right? You can generate any point in the three-dimensional space. So what are you essentially doing? You are using three vectors, three unit vectors to generate any other vector in the three-dimensional space. Okay, all right. So you have a vector v in R3, okay, which can be generated from these three unit vectors, correct? Right? Okay, so what are these guys then? First of all, these guys are spanning R3, correct? They are spanning R3, okay? Not only that, any vector in R3 can be represented by using just these three and nothing else. You actually don't need anything else, okay? So in other words, and also look at this. The reason why I chose this is because these are simple to visualize and represent. These three guys are orthogonal to each other, correct? Because this is the x-axis, y-axis and the z-axis, right? Something like this, right? So they are orthogonal to each other. And we know orthogonal vectors are, we'll show this, linearly independent. Correct. So that means, I really don't need anything else to represent any vector in R3. Similarly, if I extend this to Rn, I can actually use in other words, there is a much compact representation of this elementary vectors, right? So these guys span the vector space. Also, they are linearly independent of each other. If both things are true, then this is nothing but a basis. So what is a basis? A basis is a set of vectors which span the vector space as well as they are linearly independent of each other. It's a beautiful representation because if the guys are linearly independent of each other, then you really do not, that represents the dimension of your space as well, right? For example, in R3, the dimension of R3 is 3. Why? Because the space R3 is spanned by three vectors, as you can see, and that's enough. And these vectors are linearly independent. If the vectors are not linearly independent, the possibility is you can always have a linear combination of these two, right, and generate any other vector. Okay, all right. So in this case, the dimension of Rn is n. Why? Because it is spanned by n basis vectors. Okay, all right. So the reason why this is important is, we are talking about dimensionality, right? We're talking about the dimensionality of a matrix. So basically, all these comes from a linear transformation. So the whole idea is, when you talk about a matrix, a linear transformation, in fact, you talk about a matrix of a linear transformation. Okay. So let's see what linear independence is. Okay. So formally speaking, if I have a bunch of vectors v1 through vn, okay, and accompanied by a bunch of scalars in such a way that I write a linear combination of all that. So it's c1 v1 plus c2 v2 and equate that to 0 vector. Then this implies, the only implication of this has to be that all of these guys are identically 0. Okay, this is very, very important. I mean, how does this ensure that the vectors v1 through vn are linearly independent? Then see, it's very simple. I'll take a simple case, right? I mean, just take an example. So let's take c1 v1 plus c2 v2 equal to 0. Okay. So what happens is, let's say that c1 and c2. I mean, because according to my definition of linear independence, the c1 and c2 both have to be identically 0 so that v1 and v2 are linearly independent, right? But let's say that's not the case, right? So that means I am able to do this, okay? And then I am also able to do this. Okay, what do you see? You see that, okay, I mean, what you were supposed to do is that you were supposed to have an independent representation of V2, right? I mean, you cannot write V2 as a linear combination of, V1 or vice versa. So in this case, V1 is written as, so I can rewrite this as alpha V2, where alpha is nothing but minus C2 by C1, and alpha is non-zero. It's well defined, right? Okay, it's well defined. It's only well defined when your C1 and C2 are not identically 0. Okay, all right. So therefore, I mean, if C1 and C2 are not identically 0, you are able to express V1 in terms of V2 and V2 in terms of V1, which kills the whole linear independence concept, because when you say that V1 and V2 are linearly independent, you couldn't have expressed V1 in terms of V2 and vice versa. Okay, so I hope that definition is clear now. Okay. All right, so we're going to use all that. So we're going to use this, definition of linear. So I mean, if I formalize this, it's like Vi set of vectors I equal to 1 to n, and a set of scalars Ci, all drawn from one-dimensional real line, and we have some Ci Vi such that Ci equal to 0 for all I 1 to n. Okay, all right. So this is the formal definition of linear independence. If that's the case, then we can say that V1 through Vn are linearly independent. Okay, why we are doing this? Okay, so we are doing this for two reasons. One, I mean, just to not to refresh, but to see how some of these powerful results are used in SVD and PCA. So some of this okay. So one of the thing is, I mean, I said repeatedly, right? A set of, if the eigenvalues are real and distinct, real and distinct, then the corresponding eigenvectors are orthogonal. Okay, so let's just take a simple example, right? We know that just let's do this for two eigenvalues and two eigenvectors. So we have a T v1 lambda 1 v1, okay, and then T v2 is lambda 2 v2. Okay, this should be clear, right? I mean, lambda 1 and lambda 2 are distinct. Okay, all right. So we assume that lambda 1 is not equal to lambda 2, and v1 and v2 are the corresponding eigenvectors to lambda 1 and lambda 2. Okay. If that's the case, and we are assuming we are working on, real spaces, even if it's on complex spaces, I can use a skew Hermitian operator, but I mean, let's keep things simple. So what I do here is take a transpose on both sides. Okay. So if I do that, from the, I like transposes, and you can see why. It's simple, and lambda 1 is a scalar, the transpose of a scalar, it doesn't make a difference. I mean, you can just simply, and then you can write the lambda 1 anywhere you like. Okay. Now what we should do is, I mean, you see this equation, right? I mean infinite natural, what I can do is on the right, because when you are doing the matrix vector product multiplication, you have to be careful about the order, right? So this is v1 transpose t transpose, right? And of course, I mean, these when we are talking about these eigenvalues, we are actually talking about, we assume that these are they come from a symmetric matrix. Okay. So what this implies is that when you take the transpose of the matrix, nothing changes. Okay. So what I will do now is I'll multiply on the right by v2, the other eigenvector. Okay. Simple enough, right? But then let's look at this guy. What does this guy say? Well, this is tv2, right? I mean, t transpose, right? So I mean, I'll just get rid of the transpose. Okay. I mean, I don't, because I know that t is symmetric. So therefore, t transpose is equal to t. Okay, good. So, and then what will happen is I will use the information that tv2 is nothing but lambda 2 v2, right? So this is v1 transpose lambda 2 v2, and then I can bring everything to the one side, right? And then once again, this lambda 2, since it's a scalar, I can just write it anywhere I want. So I'll just remove it from here. Okay. And yeah, so what I have is a lambda 1 minus sorry, this is lambda 2, I'm really sorry. So this is lambda 2 minus lambda 1 v1 transpose v2 equal to 0. Good. Okay, so what do I know about this? See, I know that the eigenvalues are real and distinct, right? So I know that this guy cannot be 0, so this has to be, right? So this means that I have an inner product. I mean, what is v1 transpose v2? v1 transpose v2 is nothing but the inner product of v1 and v2, right? And that's equal to 0. Okay, so if the inner product is 0, inner product or dot product is 0, then v1 and v2 must be orthogonal to each other. What are these guys? These are nothing but the corresponding eigenvectors of eigenvalues lambda 1 and lambda 2. So we established that if we have a symmetric matrix where the eigenvalues are real and distinct, the corresponding eigenvectors are orthogonal. Fine. So what? Well, the big deal is now following this, a consequence of this result. Okay, so where did we see this? We saw this in PCA. Remember, we had that matrix 1, 1, 0.916, 0.916. We computed the eigenvalues. We saw that first of all we observed that the matrix was symmetric, and then we observed that the eigenvalues are real and distinct, and therefore the corresponding eigenvectors are actually orthogonal. So we actually did not had to compute, if that's the case, we did not have to compute the second eigenvector at all. I mean, we can just compute the first eigenvector and then easily can infer what the second eigenvector would be. So that will save some computation cost. Nonetheless, so that's one. The second one is the consequences that if that's the case, I mean, if I have a set of orthogonal eigenvectors, if I have a set of orthogonal eigenvectors, then I should be able to establish that they are Li. meaning linearly independent. Okay. How do I do that? I will leverage the idea of inner product. So I know I'll start from that definition of, standard definition of, I'll use the standard definition of linear independence. So I'll just begin by, assuming that I have a linear combination of those eigenvectors, which is 0. It means nothing until I establish that fact that this linear combination leads to only one conclusion, and that is that V1, C1 through Cn are 0. So that's what I need to show, right? So what I need to show, I know that these V1 and V1 through Vn are orthogonal, which means the inner product of Vi with Vj is equal to 1 if I equal to j, otherwise is 0. Okay, we know this. So let's do this one at a time. So let's just, as a simple example, let's just take the inner product of V1, just take one vector and just inner product it with the rest. So this is C1 V1. So we do that uniformly. So I have okay, clearly the right hand side is 0, right, and the left hand side you'll have C1 inner product of V1 with itself, and then a bunch of V1s with everything else, right? Okay. Now, since I know the Vi Vj's, this combination of vectors linearly independent of, orthogonal to each other, all of these guys are 0, right? All of these guys are 0 except this guy, because this guy is the inner product with itself, right? And because these are orthogonal, the inner product will be 1. So what that means is very simple. What that means is C1 is 0. Now this is a very simple and repetitive exercise. You replace the V1 by any vector, okay, V2, V3, V4. What will happen is, it will be shifted toward right, meaning when I write V2 here, I will naturally infer that C2 will be equal to 0. If I use V3, I'll infer C3 equal to 0. So I really don't need to repeat this. It's easy to see that everything else, C2 through C1, Cn will also be 0. That's exactly what I wanted, right? I started from here, a linear combination of all the vectors, and I show that all the scalars are identically 0. Then implies that V1 through Vn are linearly. Okay, just so that it refreshes your mind. So one final thing that I wanted to show before we move on to something else is that the whole brouhaha about eigenvalues, and we posed a question, remember, that if I have TV equal to lambda v, then why I compute the determinant and set it equal to 0 in order to compute the eigenvalues. Why do I do this? Okay, and everybody does that, right? Okay, so let's look at this idea. Let's work with this. So we have, I can see that there is an easy transposition of this from the original equation, and then I can do this, right? Okay, now let's take a moment and see what this really implies. Look, when we are computing the eigenvalues and eigenvectors, we are essentially looking for non-trivial eigenvectors, which means, look, this particular equation will be satisfied when v is equal to 0, but I'm not interested in that solution, right? For example, when you try to solve something like a system of equations ax equal to 0, you know that x equal to 0 is the trivial solution, right? Trivial, but not very useful. In other words, what you are saying is x is in the null space of A Okay, but it's a zero vector. Well, everybody knows the null space will contain the zero vector because null space is a subspace of the vector space, right? So it will contain the zero vector. But I want to know whether except the zero vector, whether any other non-zero vector is also contained in the null space of A, null space of the matrix or the linear transformation. Okay, so it goes without saying that I assume V to be a non-zero vector. Okay, all right. Now, according to the definition of null space, I can easily see that the vector V is in the null space of lambda I minus t, right? Okay. All right, and it's a null, and I also know that V is not zero, which means what? Easy to see that the null of lambda I minus t is not zero. Good. Now there is a powerful theorem which says that if the null space of a matrix, null space of this is equal to 0, then the columns are linearly independent. If it is not 0, if the null of this is not 0, then the columns of lambda I minus t are linearly dependent. Okay, if the columns are linearly dependent, that means what? I mean the rank or whatever, right? Like if the columns are linearly dependent, then you can naturally, if you take the determinant of it, it will be 0. This is the reason you solve this equation to compute the eigenvectors of TV equal to lambda, because our idea is to compute the non-trivial eigenvalues and non-trivial eigenvectors. Okay, all right. Okay, thank you.